My name is Aaron Schindler, and I'm the head of the Bioengineering and Molecular Medicine Lab at the Children's Hospital at Westmead. The title of my project is Gene Therapy to Cure Brittle Bone Disease. People don't often see children with brittle bone diseases, but for them, this has a massive effect on their life and their whole family's lives. They have to go to the hospital regularly. Whenever they fall, they risk a catastrophic fracture, and they have to repeat throughout their entire lives. To try to better understand what we say when children have brittle bones, I'd like you to imagine a building, and when you make a building, you don't just make it out of steel, you don't just make it out of concrete, you make it out of both. If you have a building which is just made out of concrete, then it doesn't have any bend to it, it'll just break. And the protein that is defective in OI, collagen, is like the steel of your bones. It provides that strength and flexibility, and when it's missing, all you have left is that concrete, and then it breaks. Our vector technology is meant to fix that collagen gene so your body is able to produce its own collagen to basically create its own steel. Current therapies only add more cement to those walls, but without steel, it's just going to still be brittle. There's over 1,000 children with brittle bone disease in Australia, and many of them will come to our hospital. So the idea of a gene therapy approach is that children who have this condition have a problem in one of their genes, and there are several genes that can be affected, that leads them to have bones that break more easily. That's because protein collagen is usually defective, and we can fix that now with gene therapy approaches. However, currently there's a real need to develop vectors to be able to deliver those to the bones of these children. So a vector is, in our case, a virus. But unlike viruses that try to make you sick, like COVID-19, for example, these viruses are genetically engineered to make you better. So the way that a virus can make you better involves a technology that was only invented within the last 10 years called CRISPR. CRISPR is a way for genes to be edited, and by taking the bits of the virus that would cause disease and replacing them with machinery, this CRISPR machinery that we can target to edit and fix genes, then we can repair throughout the entire body, hopefully, a child and be able to have them have a completely normal life moving forward. I run the team, and I have 17 years experience in bone and bone disorders as a postdoctoral scientist. Also, we have orthopedic surgeons and clinicians who specialize in endocrinology on our team, and we also have people who do molecular biology and gene therapy. So we've spent the last 3 years developing key technology to be able to deliver vectors directly to bone and bone cells. However, our research is now fall into what they call the research valley of death, which is between the basic discovery research and being able to get this translated into clinical practice. There's a whole lot of work that needs to be done in terms of safety and technological development that needs to bridge that gap and be able to get this into children. One of the big advances that we've made recently was published in one of the Nature family journals, the Molecular Therapeutics Journal, and in it we describe how we've been able to take a virus and show that we've managed to be able to transform all bone cells in a preclinical model and change their genes simultaneously with a single injection. And this is the first time anyone in the world has done anything like this. So this points towards the idea, again, of the efficacy of these vectors. There is currently this big gap between the theory behind editing genes and practice of being able to actually edit genes. And that we worked out many years ago that this is a gap that needs to be filled and that we were the lab to be able to fill it. So the way the vectors work, we've had to optimize two separate things. So the first is, like all viruses, they have a coat on them, which determines what cells they're able to get into. And we've screened a host of different coat proteins to find ones that are very efficient to getting to bone. Then we engineered tag DNAs, which limits the expression to just bone. So we have something that can get into bone and then is very specific for bone. One of the great things about working with vectors and vector technology is the fact that the CRISPR that underlies the gene editing is moving so fast. So anything that we do which creates something with tissue specificity, it means that we can almost instantly integrate any new discoveries that happen around the world in the gene editing section, and then that will make our vectors more effective And that's something that we're really excited about. The earlier and faster we can get these therapies online, the faster we can be able to help these children. The problem that we've always had since when I started doing research was that it was very easy to work out what gene problems existed, in that we could see changes were happening, but often it was hard to do anything about it. And now, with the technologies that have been exploding around the world over the past 5 to 10 years, we're beginning to reach a stage where we can actually do things about that. The other reason that I think this is urgent is because in parallel, we're developing this technology for a range of other diseases. Brittle bone disease is our focus and the one that's ahead, but we're confident that other genetic diseases like muscular dystrophy could be amenable to these sorts of therapies. And this gives us an opportunity to be able to do something which will be truly transformative for them. Our team are world leaders in this area, and while we appear to be from a small lab in Sydney, in many respects, we are pioneers in this technology. And with our collaborators and other people who support us in the Westmead area, with some investment, we would be able to make some paradigm shifting changes in the way that we treat children with genetic diseases.